Welcome to the ECOM 3313 Microwave Engineering course. So this would be your Lecture 1, the introduction and the overview of pertinent electromagnetics. In this microwave engineering course, we will focus primarily on the electrical circuits that operate at frequencies of 1 GHz and higher. So in terms of band designation, we will be working with circuit that is above UHF, ultra high frequency. So if you refer to this table, you have the RF region, the radio frequency region that starts from 3 MHz up until 1 GHz. So this will include the HF band, high frequency band, VHF, very high frequency, and UHF, ultra high frequency. Next, the microwave region. So microwave region would start from 1 GHz up until 40 GHz. So the band for microwave region is L, S, C, X, KU, K, and KA band. So in terms of wavelength, you will have lambda that starts from 30 centimeter. So when you have lambda equals to 30 centimeter, this will refer to the 1 GHz up until 8 millimeters. So when you have the lambda is equal to 8, that would refer to the 40 GHz. So above the microwave region would be the millimeter wave region. So millimeter wave region starts from 40 GHz up until 300 GHz. So the band that we will look into is the V band, W band, and also the millimeter band. Now, the advantages of microwave circuits. So we have a few listed here. So the first one, the gain of certain antennas increases with reference to an isotropic radiator with its electrical size, meaning that you can construct a high gain antenna if you use microwave frequencies. So usually for lower frequencies, the gain is not high compared to the microwave region. Number 2, more bandwidth. So a 1% bandwidth will provide more absolute frequency range at microwave frequencies if you compare to the high frequency. Number 3, the microwave signal would travel predominantly by line of sight, meaning that you don't have much reflection like what you have with high frequency signals. That's why the communication link would use microwave frequencies, which is the higher frequency, 1 GHz and above, between satellite and terrestrial stations. Number 4, at microwave frequencies, the electromagnetic properties of many materials are changing with frequency, meaning that this behavior is useful for remote sensing and other applications. And lastly, there is much less background noise at microwave frequencies compared to radio frequencies. So for wireless data networks that uses microwave frequencies, we have Bluetooth, Wi-Fi that uses the IIUM standard 802.11, and then we have WiMAX that use the IIUM standard of 802.16, Zigbee, GPS, cellular telephones, and so more. So these applications are using the microwave frequencies. So can you think of some others? So maybe in next class, you can provide me what are the actual frequencies that is used by all this application. Now, the disadvantages of microwave circuit. Okay, microwave circuits are much more difficult to analyze than low frequency ones. So why? So here we have listed a few. So the first one, voltage is not well defined if the distance between the 2 points is not electrically small. So at microwave frequencies, electrically large distance may be just a few millimeters, meaning that if you move the probe around just a little bit, it will also likely to affect the voltage measurement. Next, you have to carefully choose the lump elements. So what are lump elements? You have L, the inductor, C, the capacitor, R, the resistor, the diodes, the transistors, and so on. If you want to use the microwave region, because you are dealing with very high frequency. So that's why you have to choose it very carefully. So for typical low frequency components, it does not behave as expected. Okay, you don't have this kind of problem for low frequency components. Number 3, to transport electrical signals from one position to another, one must use special wires. So for microwave circuits, you have to use special wires or the guidance signals that are very much different for the low frequency items or components. Now let us look into the EM. So EM is electromagnetic phenomenon, which involve forces that produced by stationary and moving charges. So low frequency circuits are generally very, very small with respect to the smallest EM wavelength present in the circuits. So that's why simple lump element circuit models can be used to describe the EM effects of resistors, the inductors, capacitors, the voltage and current resource. So at microwave frequencies, the circuit may not be electrically small. Okay, so it requires a shift in our approach to the EM analysis. So nevertheless, the electrical signal remain the outcome of EM phenomenon. So perhaps the two most important of the Maxwell equations would be the Faraday's law and also the Ampere's law. So you should know it in the differential and also the integral form. So much of our work in this course will be in the sinusoidal steady state. So of course, both the differential and integral forms are equally valid. So which of these to use depends on the problem. So if you want to derive the equation to solve for the electrical and also the magnetic, the differential forms are often better. But for circuit approximation of device or other physical interpretation, the integral forms are often more useful. So worry not, rather than using the full-blown Maxwell equation in the microwave circuit design, approximations are often used in order to simplify the solution. So that's why in this course, we would pretty much look into the approximations.